Diamond Age is built on a simple premise. Modern science is no longer limited by imagination. It is limited by scale, integration, and participation. Across today's research ecosystem, we generate unprecedented volumes of data, yet our ability to interpret, simulate, and translate that data into real-world decisions remains fragmented. Digital twins represent a paradigm shift, not as static simulations, but as living, adaptive computational mirrors of real systems, capable of prediction, steering, and optimization in real time. Diamond Age extends this paradigm into biology, materials science, and human skin, transforming digital twins from industrial tools into interactive worlds where discovery becomes playable, scalable, and collective. Slide 2. Agenda. This presentation follows the same logic as a scientific pipeline. From problem definition to system architecture, to implementation, and ultimately to societal impact. We begin by examining the chemical and biological reality of tattooing, an ancient practice that has quietly become one of the largest unregulated material experiments on Earth. From there, we introduce digital twins for science, an emerging framework designed to unify simulation, data, artificial intelligence, and control, particularly in domains where traditional experimental cycles are too slow, expensive, or ethically constrained. Finally, we show why massively multiplayer systems are not a gimmick, but a proven scientific strategy for navigating vast design spaces, and how Diamond Age converts play into validated scientific insight. Tattooing is often framed as art or culture, but at a molecular level, it is a permanent intradermal implantation of engineered particles. Modern tattoo inks contain pigments originally developed for industrial applications, automotive coatings, plastics, and printing inks, not for long-term residence inside living tissue. These pigments frequently exist at the nano-2 microscale, enabling migration through the lymphatic system, interaction with immune cells, and chemical breakdown under ultraviolet radiation. Problem statement. Unlike pharmaceuticals or medical implants, tattoo pigments are not subjected to pre-market approval pipelines. In the United States, the FDA technically holds authority over tattoo inks, yet no pigments are formally approved for intradermal use, and enforcement remains reactive rather than predictive. European regulatory bodies have acknowledged this gap, noting that conventional toxicology frameworks cannot be directly applied to tattooing without validation, because tattooing represents repeated particle injection across the skin barrier, not topical exposure or ingestion. Solution Diamond Age exists precisely to fill this void, not by replacing laboratories, but by augmenting them with digital twins capable of exploring what experiments cannot yet reach. Traditional toxicology was designed for short-lived exposures, not permanence. Tattooing violates core assumptions of standard safety pipelines. Pigments are injected directly into the dermis, remain for decades, and are continuously exposed to ultraviolet radiation that can induce photochemical breakdown into secondary compounds with unknown toxicology. Each ink is not a single chemical, but a system of materials whose behavior emerges from interactions rather than isolated components. Product. Digital twins emerged in aerospace and manufacturing as a response to similar complexity. A digital twin is not a static model. It is a bidirectionally coupled system, continuously updated with data from its physical counterpart and capable of prediction and intervention. For tattoo pigments, this means constructing multi-scale twins that integrate molecular structure, particle behavior, tissue optics, immune dynamics, and environmental exposure within a continuously refinable computational framework. Diamond Age operationalizes this concept by embedding these twins inside an interactive environment, where hypotheses are not only tested by machines, but stress-tested by human intuition at scale. Market. The rise of digital twins for science coincides with a deeper transformation in high-performance computing. The post-exascale era is defined not by larger single simulations, but by ensembles, AI-accelerated inference, and real-time interaction. Classical ab initio chemistry methods offer accuracy, but cannot support real-time interaction across large design spaces. Machine learning shifts this balance by learning surrogate models from high-fidelity simulations and experimental data. Diamond Age leverages this philosophy deliberately. Physics where needed, learning where possible, and humans where intuition outperforms brute force. Market opportunity. At first glance, a game may seem orthogonal to science. In practice, games are among the most efficient systems humanity has ever built for exploring large, ill-defined problem spaces. The Foldit project demonstrated this clearly. Non-experts solved protein structures that resisted automated algorithms, directly contributing to peer-reviewed discoveries. Business model. In Diamond Age, every player action is data. Choices about pigment structure, particle size, layering, or exposure conditions are logged, analysed, and fed back into the digital twin infrastructure. This creates a virtuous cycle. Human intuition guides exploration, machine learning refines prediction, and digital twins validate emergent hypotheses. Metaverse monetization model. One of the most powerful enablers of Diamond Age is a counterintuitive discovery in artificial intelligence. Toxicity can be predicted from images alone. Deep learning models trained only on molecular drawings can internalize latent chemical features directly from structure. As players design pigments, AI models provide real-time feedback on predicted toxicity endpoints. Safety becomes an interactive design constraint, not a downstream regulatory hurdle. Product mock-up. Researchers. The skin is not a passive barrier, but an active, information-rich interface between the body and the environment. Research such as MIT Media Lab's Dermal Abyss demonstrates that tattoos can function as biosensors, responding visibly to changes in physiology. Product mock-up. Tattoo artists. Beyond sensing, intradermal pigments can actively protect the body. Research into UV-protective tattoo pigments shows that materials can be engineered to absorb and dissipate ultraviolet radiation without altering visible skin color. At the nano-scale, particle size, encapsulation chemistry, and photostability determine whether pigments protect or harm. Diamond Age enables these distinctions to be explored computationally, optimizing safety, longevity, and function simultaneously. Diamond Age is not simply software, it is a new scientific instrument designed for an era where complexity exceeds the capacity of any single lab, algorithm, or discipline. By combining digital twins, AI, and massively multiplayer collaboration, Diamond Age transforms how we explore biological materials, reason about safety, and distribute the labor of discovery. This is the Diamond Age, not built in isolation, but played into existence.